So, last installment. Yesterday we went through some kind of derivation, still very hand-waving, but I hope it gave some idea of the technical underpinnings of this renormalized Landau free energy. So the upshot was that if we treat the magnetic order parameters still in midfield approximation, but do a much better job on the fermions than in the Hertz-Millis-Moria theory, then we find this non-analytic term in the Landau free energy density that is in between a quadratic and a quartic term, comes with a negative sign, and as a result, our phase transition is first order. Then we discussed that a bit, and in particular, so here are the consequences, and in particular, we discussed a little bit why there are at least some reasons to believe that this result is actually more robust than corresponding results in classical phase transitions, and that has to do with the upper critical dimensionality of the decoupled bosonic degrees of freedom and the dimensional reduction in the quantum case. And this is where we got stuck. So now it's, after all, the school has a disorder theme, so we should talk about disorder a bit. Before I get into that, any questions so far? Yes?
I guess I understand the way the calculation is done, but I have no intuition for this. What is happening? What gives you the non-analytic term? What are the fluctuations that come?
Okay. It's the same particle hole excitations that are soft at zero temperature that lead to the T cubed log T term in the specific heat, or the K squared log K term in the spin susceptibility. So all these things that produce non-analytic behavior in the next to leading terms in the in Landau Fermi liquid theory. Okay? That's these same soft modes. Now, when you do Landau Fermi liquid theory, it's not quite apparent where these things are coming from. Okay, they just pop out of the theory. If you do perturbation theory, it's very unobvious where these things are coming from. Okay, so you calculate the diagrams, and some cancel and some don't, and there it is. Okay, so the part of what I was trying to advertise here is that the field theory actually gives you an idea of the physical underpinning of these effects and its soft modes. And you can interpret them as Goldstone modes. You can interpret the Fermi liquid phase as an ordered phase in the technically precise sense. And that's unfamiliar, and that's why most people show that reaction. They say, what are these things? Okay? So, and then again, if for those of you who are old enough to remember the weak localization business, right? So diffusons were very popular in that context. It's the clean analogs of the diffusons. It's the exact same correlation functions. Only now they have a ballistic spectrum rather than a diffusive one. Oh, and that reminds me. So Alex pointed out to me that I've been sloppy when I talked about the propagators, and he's absolutely right. I was. So I had a slide that had things like, remember, so our little q and m were isomorphic to psi bar and psi m, with n greater than 0 and m less than 0, or vice versa. And then I wrote down the correlation functions like this, and very sloppily, I should put a wave number in here. And then very sloppily, I wrote them as 1 over mod k plus omega n minus omega m, okay, stuff like that. Well, I'm lying here. That's not true. What's actually happening, so this is a bosonic frequency, omega n. What's actually happening is this is a 1 over mod k times a function that depends on dimensionality. That's a function of Vf mod k divided by omega n. Okay? So it's something that scales like this, but it doesn't look like this. And this function, one can calculate. It's fairly complicated in generic dimensions. You can express it in terms of hypergeometric functions. But for the purpose of this entire scaling argument, it doesn't matter whether it really looks like this. Only thing that matters is it scales like this. Okay? And again, in the disordered case, what would happen is you would get a 1 over dk squared times something else that depends on dimensionality. That's dk squared over omega, and d is the diffusion coefficient. Okay, so this is clean, and this is disordered. Okay. Anything else at this point before we proceed to the disordered case? Yeah. Yeah.
From this formalism, it does not look like there is not anything special about the existence of a surface like the Fermi surface, right? I mean, one can read these bilinears out of any fermions that we have, and then do the theory in terms of the bosons. So why don't, I mean, is it a popular thing to see it when the expected Fermi state is not a Fermi?
Yes, yeah, okay. So the existence of the soft modes, for instance, is tied to the existence of a Fermi surface. If you don't have a Fermi surface, what happens okay, so here's one way to say it. What happens effectively is that in this cartoon representation of the soft mode, the numerator is not 1. The numerator is actually the wave function renormalization. Okay? And if you don't have a Fermi surface, that thing goes to 0. Then you have a 0 weight of your soft modes, and everything changes. So, for instance, if you try to do the same thing in, let's say, a Weil semimetal, okay, then things are very different because of that. So it does rely on the Fermi surface.
So the assumption there is the soft modes exist at this Fermi surface.
It's not that's not an assumption. It's a stronger statement. The statement is if you have a non-zero spectrum at the Fermi level, a non-zero spectrum of the Green's function at the Fermi level, then these things exist. And they do couple to the magnetization.
Yeah.
Okay, so it's an if-then statement. And if you throw out the Fermi liquid, then you have to rethink everything. Okay. Yes? Can I explain phi? Okay, this guy? Okay, it's some function that depends only on this combination of arguments. It's a function of k over omega, okay? It doesn't, for our purposes, it doesn't matter what the function is. If you want to know it, you can calculate it, and you can look it up in one of our papers. Okay? It's a complicated function in terms of hypergeometrics. Okay? But the only important thing here is that k scales like omega, just like here, k scales like omega. Okay? So there is this, what we discussed yesterday, there is a dynamical exponent z that's equal to 1 that's tied to the fermions. And then there's another one that's z equal to 3 that's tied to the bosons. So again, that's the that's the beauty of scaling arguments. That's once you figure out how things scale with each other, you don't have to worry about details. Okay? Cool. Then let's turn on disorder. So it turns out that disorder changes things in a rather drastic way. So if we remember how we argued the non-analyticity in the renormalized Landau free energy came about, that was ultimately we tracked it down to a non-analytic magnetic field dependence of the fermionic spin susceptibility. And in the clean system, that went like constant plus field to the d minus 1. Okay? And if you repeat that calculation for a disordered Fermi liquid, then you find it goes like constant minus h to a different exponent, d minus 2 over 2. Okay? The over 2 comes because now k squared scales with omega, okay, rather than k scaling with omega. And the d minus 2 rather than d minus 1 reflects the fact that the lower critical dimension now had better be 2, because we know that disorder in 2 dimensions localizes everything, the physics changes. Okay, we don't have a nice disordered Fermi liquid fixed point anymore. This actually has also been known for a long time. I mean, you can trace that back to the early 80s when it was calculated in perturbation theory. And again, a renormalization group tells you that the exponent is actually exact. And again, note the sign. So if we go through the exact same arguments as before, then of course we get still a non-analyticity. Of course, the exponent changes because the exponent here is different. It's now 5 over 2 in 3 dimensions. And the sign will change. So now our non-analytic term in the free energy density comes with a plus sign. And that means that the prefactor is still positive in this notation. So that means we now have a second order transition, but with non-mean field critical exponents. Okay. So in the clean case, the coupling of the order parameter fluctuations to the extraneous, the fermionic soft modes, is so strong that it actually changes the order of the transition. Here, it changes things quite dramatically from mean field exponents to something very non-mean field. But it doesn't manage to change the order of the transition. The transition remains continuous. Okay? So that's the upshot. So because of this important difference, I owe you at least a hand-waving explanation for what causes the sign change, right? That would be nice to understand. So here is how we can make that plausible. Let's look at the spin susceptibility of a Fermi liquid in the clean case versus magnetic field. So let's first go to zero magnetic field. If we have non-interacting fermions, then we've got the Pauli susceptibility here. Okay, so that's what we calculate in our undergraduate StatMech class. Now, if we switch on interactions / fluctuations, the fluctuations will suppress the tendency of the electrons to ferromagnetically order. Right? So fluctuations are not good for order. So fluctuations bring down the value of the spin susceptibility to something less than the Pauli susceptibility. Now, a magnetic field gives these soft modes that represent the fluctuations a mass. and therefore a field suppresses the fluctuations that suppress the spin susceptibility. So as a function of field, the spin susceptibility must go up. And it does, as we've seen last time. In the disordered case, it's more complicated. Because what happens is that there is a strong interplay between the quench disorder, the static fluctuations of the quench disorder, and the electron-electron interaction. So that's what Altshuler and Aronov were looking at starting in '79, and which then was pursued by many people for many years. It's well known that this combination of disorder and electron-electron interactions leads to an increase in the spin susceptibility. So fluctuations, meaning disorder plus interactions, actually increase the spin susceptibility from the Pauli value. And incidentally, that is what's behind the infamous runaway flow in Finkelstein's nonlinear sigma model, and so on and so forth. So there's a long disorder physics history of this. Okay? So that's well known. Now again, the field suppresses these fluctuations because it gives the diffusons in this case a mass. And so, as a result, the thing will go down, and it does. Right? So that's, in a nutshell, the crucial difference between the clean and the disordered case. The exponent, the difference in the exponent, that's a detail. But the difference in the sign, that's absolutely crucial, because that makes the difference between a first order and a second order transition. So, given that, we can now it's extremely easy to analyze this theory. So you can do that in your head, right? So if you put h equal to 0 and differentiate with respect to m, find the minimum, you instantly see m goes like t squared. Okay? So we have an exponent beta that's equal to 2. And that also means that the Curie temperature will go like distance from critical point squared. Let me just show you this uranium, thorium, nickel, silicide phase diagram again here. So the author of that paper actually advertised that as an example of what Thomas showed us yesterday. Okay, so smeared transition in the sense that Thomas explained. If this is all you know, and actually for this material I think that is all that's known, then I'm not sure I'm convinced. I mean, I would say this can just as well be interpreted as a beta equals 2. Right? You need to know more in order to tell which, if any, of these two explanations applies here. Okay.
It's only fair to point out that in your theory, the random mass term is not there, right? So the entire physics I was talking about is just not built in.
Well, that physics is not built in. That's correct. That's correct. Yes. Yes. I mean, the random master. Yeah. Okay. You can say the random master. I would say that. I mean, rare regions are not there. Yes. True. True. Yes. So there's additional physics. Okay. And that additional physics is not in any obvious way coupled, actually, to the physics that's described here. So these two things may well come on top of one another and make the interpretation of experiments rather tricky. That's absolutely true. Good. So now, next question. What if we start with a clean system and gradually introduce a little bit of disorder? Well, here's what you would probably guess. And what happens, you can work that out, and one of my students did so for her thesis. So what happens is, as you introduce disorder, the tricritical temperature marches down, the wings shrink, and at some point you actually do recover a quantum critical point even in zero field. Okay. And again, what exactly is going on there is probably complicated because there's all these different types of physics coming in. So yeah, in particular, the effects that Thomas talked about yesterday. And so the actual complete theory is probably very, very complicated. And here's that experiment on uranium nickel silicide again. And here is another experiment that I had shown before, and Thomas had shown the same data, I think. So here you see some additional information. As not this material, it's a different material. But here you see additional information that gives you a clue as to what may or may not be behind the shape of the phase diagram. So in this case, it's a very weird field dependence of the magnetization. Okay. So there's still a lot to be done in that area. Yeah?
The UM4 that you have written down is schematic. It's a schematic UM4, right?
Wait, let me go back to that.
This UM4 is actually a schematic UM4, right?
In schematic in which sense?
In the sense that if you write things down with replicas and things like that, there will be.
Yes.
Right?
Right.
Yeah,
But that's the mean field theory. That's the mean field theory.
I completely agree. But what I mean to say is, in Thomas's question, right? If you really do it before you take the mean field limit, there are two types of U-term.
That's true too.
Yeah.
That's a true statement.
Yeah,
but that's not what Thomas was saying.
No, but what I'm saying is that if you do that, and if you
Yes.
then think of the second term, that
Yes.
one which is phi alpha square, phi beta square, that is one that is produced by a random mass term usually.
Yes, but okay, that thing is actually irrelevant with respect to this fixed point. But in addition, there are more subtle effects of the disorder, and they are not included in here. Okay, but since you're prompting me here, so for the disordered case, as you know, we've actually analyzed the actual coupled field theory in some detail, right, with Maria Teresa Mercaldo and Sharon Sessions. And have done a renormalization group analysis of the coupled field theory without integrating out the fermions. Okay, so there's a lot more known about this theory here than this slide implies. Okay. We lost a fan. Okay. Good. So that's my tribute to disorder. Sorry, I never know which is which. Okay. Yeah. This is where we were. Good. Cool. So that was the tail end of the nominal lecture 3 that I didn't quite get through last time. So now let me step back and talk a little bit about continuous phase transitions while we are on the topic in the context of the disordered quantum ferromagnet. So if we have a continuous phase transition and we go into the quantum limit, then what do we have to worry about and what do we have to change with respect to what we know about classical continuous transitions? So to motivate this discussion, so for instance, how many critical exponents do we need? How many of these are independent? Okay? So those are important questions for both the theory and for analyzing experiments. So just to motivate this discussion, here is again this experiment on nickel, aluminum, gallium, which shows what for all intents and purposes looks like a continuous phase transition. Okay. So let's remember how we define critical exponents in the classical case. So classically, we have a non-zero critical temperature, Curie temperature in this case. So suppose we are here at some x well below the critical one. We have a thermal transition. Okay? So as we approach the critical temperature, from below, let's say, our magnetization goes to 0 with a power law that's characterized by an exponent beta. If we are sitting right at the Curie temperature and switch on a magnetic field, then our order parameter, the magnetization, goes like the field to some power that's called 1 over delta. So that's another critical exponent. It's for historical reasons, it's 1 over delta. Yeah, that's just what it's called. The susceptibility diverges with an exponent that's called gamma. The correlation length diverges with an exponent nu. And the specific heat either diverges or shows a cusp with an exponent called alpha. Alpha can be positive or negative. If it's positive, then it diverges. If it's negative, it has a cusp. OK, so that's all very well known. Now, if we look at the quantum phase transition, then things get more complicated. So now what we can do, for instance, is we can, let's go back here, we can sit at criticality, let's say at 0 temperature, and now we can approach the transition or go away from it either by staying at 0 temperature and vary the control parameter, or we can vary the temperature. And that's physically very different. So here, there are no thermal fluctuations. If we switch on a temperature, there are. So the order parameter how the order parameter behaves will depend on how we approach the transition. And so we need more exponents. So for instance, here, at 0 temperature, as a function of the control parameter little t, which is now non-thermal, it will go like minus t to the beta. But at criticality, as a function of temperature, it will go like temperature to a different exponent. Let's call that beta t, beta cap t, okay, to indicate the fact it's still an order parameter exponent, but it's tied to the temperature dependence of the order parameter rather than the little t dependence. Okay. So here's an extra exponent compared to a classical transition. Similarly, the order parameter susceptibility at 0 temperature, we define an exponent gamma by saying how it diverges as a function of the non-thermal control parameter. And we define an exponent eta by saying what the wave number dependence of the order parameter susceptibility is at 0 temperature and at criticality. But if we sit at criticality and increase the temperature, then our susceptibility will show a power law dependence on temperature, and that's again given by a separate exponent. Let's call it gamma t. Okay. Same thing with the correlation length. There is a nu that describes what happens at 0 temperature, and there's a nu t that describes what happens at criticality as a function of temperature. With the specific heat, it's a tiny little bit more tricky. So the specific heat, of course, vanishes at 0 temperature. It's the third law of thermodynamics again. So it's not a good idea to consider the specific heat. Let's consider the specific heat coefficient. So let's divide by temperature and look at gamma, the specific heat coefficient. So gamma is the thing that multiplies temperature to give the specific heat. So C is gamma T, and near the phase transition, this will become T dependent. And so then we can define an exponent that I call alpha bar. that describes the zero temperature dependence of the specific heat coefficient, and an alpha bar T that describes the temperature dependence at criticality. And if we go to a thermal transition, then of course to leading order, this T just becomes a TC, and then it doesn't matter whether or not we pull out that temperature. So classically, alpha bar is equal to alpha. Okay? That becomes the ordinary specific heat coefficient exponent. Cool. Now, on general physical grounds, because of the different nature of the fluctuations at zero temperature and finite temperature, we expect that these exponents that come with subscript cap T are different from the ones at zero temperature as a function of linearity. So what is the relation? And I must apologize on this slide, which I pulled out of something different. I call the zero temperature distance from criticality little r, as Thomas did. Okay, so I'm switching notations here. Little r equals little t. Cap T is the temperature. So in general, the answer is actually complicated. But let me give you some idea of the direction in which this is going. So as we've seen several times in several of these lectures, what's characteristic about quantum phase transitions is that we cannot talk separately about statics and dynamics. So we need to discuss the dynamical scaling together with the static scaling. And so we have a relaxation time that goes like the correlation length to n a dynamical exponent z. And we have power laws that result from homogeneity laws in general. Okay, that's not always the case, as we've seen in Thomas's lecture. But suppose we do have a kind of standard transition where a generalized homogeneity law holds. Then suppose, so what would that look like? So suppose we have some observable that I call curly O here. And we look at it as a function of distance from criticality at zero temperature and temperature. And a typical homogeneity law would look like this. It's the scale factor B to the power minus omega over nu. And omega is an exponent that's characteristic of our observable. It's the scale dimension of the observable. And then comes a scaling function that contains the scaled versions of R and T. And R, by definition, comes with a b to the 1 over nu. That's the definition of the correlation length exponent. And T comes, by definition, with a b to the z. That's the definition of the dynamical exponent. And as you will notice here, I'm implicitly assuming here that there's one and only one dynamical exponent. And we already know that's in general not true. But let's ignore that for a second just to make a point. Okay? So suppose there's only one z. Or suppose that for the purposes of the asymptotic behavior of this observable, we need to consider only one z. And that's this z. Okay. So then, if I put b equal to r to the minus nu, this argument goes away. And the observable at zero temperature scales like r to the omega. Okay. So that's the exponent that comes with this observable. At criticality, we put r equal to 0. We put b equal to t to the minus 1 over z. And then we get a power law dependence of the observable on the temperature. And that power, of course, is equal to omega over nu z. So in this simple case, we have a definitive relation between the exponent that characterizes the temperature scaling of our observable and the exponent that characterizes the static or zero temperature scaling of our observable. And the two are related by the product of the correlation length exponent and the dynamical exponent. So that's a basic observation. And now complications kick in. So as I already said, in general, there's more than one Z. So in the example of our metallic ferromagnets, there's at least one Z related to the electrons and at least one Z related to the order parameter. And so it's not that simple. And then dangerous irrelevant variables can come in and screw up the simple argument. So one needs to be more careful in general. Okay. But the an underlying relation like this always remains. Now, that brings us to the next point. So here I just argued that discounting complications due to multiple Z's, there's a one-to-one relation between the omega and the omega t. So omega t is not an independent exponent. So how many independent exponents are there? Well, let's first remember how many independent exponents are there at a classical transition. So to remind ourselves of that, let's go back to the homogeneity laws. So forget quantum for a second. Let's look at a classical order parameter, for instance, a classical magnet, as a function of now little t is little t again. Okay. As a function of t and h. And here's our generalized homogeneity law, okay, that we can derive from the RG if we like, or we can just take it as a phenomenological fact. And you see the exponents have been, so that's by definition nu. What is the scale dimension? Oh, and this one is by definition beta. That's the scale dimension of the order parameter. Now, what is the scale dimension of h? Well, that we must choose such that at criticality, m goes like h to the 1 over delta. And if you require that, then you see the scale dimension of h must be beta delta over nu. So that actually works, right? So let's try it out. Just make sure it works. So we have, which one do we want? M. So m of t and h is equal to b to the minus beta over nu. And now, how do I write it? I write it as a scaling function phi m of t b to the 1 over nu, and then h b to the beta delta over nu. So now, let's put b is arbitrary, it's an arbitrary scale factor. So let's put b equal to t to the minus nu. That's because we can make it equal to anything we like, anything positive. Then we get that m of t and h is equal to b is t to the minus nu, so that becomes t to the beta. And by the way, I'm not distinguishing between t and mod t here for this purpose. Then I get phi m of 1. That's how I've chosen b, so that's what happened. And then we get h to the h divided by t to the beta delta. So in particular, at h equal to 0, this turns into t to the beta, which is the definition of the exponent beta. So that works fine. Now, let's put b equal to h to the minus nu over beta delta. Or alternatively, I can just go to t equals 0. It doesn't matter which order I do this in. Then I get m of t and h is equal to h to the power 1 over delta times phi m of t times h to the minus 1 over beta delta, and the second argument is 1. And you see if I put t equal to 0, then it goes like h to the 1 over delta. And that's the definition of the exponent delta. Okay. So that's how this scaling business works. Now, let's look at the susceptibility, the order parameter susceptibility. So that's the derivative of m with respect to h. And let's go into our homogeneity law here and perform the differentiation at this level. Then, if I differentiate with respect to h, what happens is I bring out a factor of b to the beta delta over nu. So chi of t and h, which is the mdh, that will obey a homogeneity law that looks like this. I've got a b to the beta over nu times delta minus 1, combining these two factors, times another scaling function, let's call it phi chi, of the scaled arguments. Okay. So that's the corresponding homogeneity law for the susceptibility. But now you see, by definition, this must be b to the minus gamma over nu times phi chi of the scaled arguments. Because gamma is the exponent that describes this divergence of the susceptibility as a function of little t. So we see gamma is not independent. Gamma must be related to beta and delta. And if you just compare this line with that line, then you see obviously gamma is equal to beta times delta minus 1. Okay. So that gives us a relation between exponent that's known as Widdom's equality that was found empirically before the renormalization group. Unfortunately, by the way, in the literature, these exponent relations are often referred to as scaling laws, and the homogeneity equations are referred to as scaling laws. So if somebody says there's a scaling law, you never know what they mean. So it's good practice to call these exponent relations and these homogeneity relations, but hardly anybody ever does. And clearly you can play this game with other thermodynamic observables. So if you do, then you find a whole bunch of these relations. So for instance, you also find that alpha, the specific heat exponent, plus 2 times beta plus gamma is equal to 2. That's known as the SM-Fisher equality. And you find a relation between gamma, again, the susceptibility exponent, eta, the exponent that describes the susceptibility dependent on the wave number at criticality, and the correlation length exponent. So gamma turns out to be 2 minus eta times nu. That's known as the Fisher equality, and so on. You can play this game and derive a bunch of these things. So they are far from all independent. And furthermore, you also find some of these relations that depend explicitly on the dimensionality of the system. So here you see these 3 examples just relate exponents to one another and to numbers, 1 and 2. Whereas there are other relations, for instance, this one here, nu times dimensionality equals 2 minus alpha, that's explicitly dependent on D. These kind of relations have a special name. They come under the name of hyperscaling relations. And it turns out that the ones that don't depend on the dimensionality are more robust. So if you check it, for instance, for mean field theory, let's do that real quickly. In mean field theory, alpha is 0, beta is 1/2, gamma is 1, 2 times 1/2 plus 1 is 2. Works. If you check it for the 3D Heisenberg ferromagnet, the exponent values are weird, but it still works. Okay. Or the Fisher inequality, eta is 0 in mean field theory, nu is 1/2, 2 times 1/2 is 1, gamma is 1, works. Okay. This guy here, nu times d is 2 minus alpha. In mean field theory, alpha is 0, nu is 1/2, doesn't work. Okay. So what happens is that the hyperscaling relations, that's why they are called hyperscaling, they rely on a stronger scaling assumption than the other ones. And as a result, they do not work above an upper critical dimension. Okay. So they work only below 4 dimensions in the case of a Heisenberg ferromagnet. They do not work for d greater than 4. That's important for quantum phase transitions because, as we've discussed, the upper critical dimension for a quantum phase transition tends to be much lower than the one for a classical one. Okay? So one has to be extremely careful about hyperscaling. It generically does not work. Okay. Anyway, so if you play this game, then at the end of the day, for a classical phase transition, you find of all this plethora of critical exponents, only 2 are independent. More precisely, 2 static ones are independent. If you're interested in the dynamics, you have to consider that separately. But as far as the thermodynamics are concerned, 2 exponents are independent, and the others are all related via these exponent relations. Now, just another general comment here. So as we've seen in Thomas's lectures, especially yesterday, there are phase transitions where this kind of simple power law scaling doesn't work. Okay? The observables do not obey just a simple homogeneity law. Things are more complicated. And so then what happens? Well, turns out one can still say a bunch of things based on thermodynamics only. Okay, so now I'm kind of getting back to the topic of my colloquium. So for instance, turns out if you take the SM-Fisher equality alpha plus 2 beta plus gamma equals 2, then that relies on scaling being valid, on some homogeneity law being fulfilled. Whereas one can show based on thermodynamics only that there is a rigorous inequality, alpha plus 2 beta plus gamma must be greater or equal than 2 no matter what. And if simple scaling holds, then the inequality becomes an equality. So that thing is known as the Rushbrook inequality. And it played an important role, actually, early in the development of critical phenomena. There's a famous story where some experimentalists showed data and said, here I've measured critical exponents, and here they are. And Rushbrook was in the audience, and Rushbrook gets up and says, that's wrong. Right? And turned out he had derived the inequality, hadn't published it yet. So he could instantly tell that whatever the experimentalist was measuring could not be the actual critical exponents because it violated thermodynamics. Okay? So that's a powerful tool, that kind of thing. And while I'm on the topic of inequalities, let me also advertise this one again that we've seen before. So Thomas derived and discussed the Harris criterion, which refers to the exponent nu at the fixed point describing a clean system and has to do with the stability of that critical behavior with respect to disorder. Now, turns out that there is, again, a rigorous, in the mathematical sense, rigorous lower bound for the exponent nu at any second order transition under very general assumptions, which I'm not going to get into. So that nu is, yeah, any disordered, I'm sorry, at any disordered fixed, that's important. Yes. So whenever you have quenched disorder, and then there are subtleties with respect to how one should properly define nu. Okay, fine. In any case, this nu is not tied to some fictitious fixed point that may or may not be stable. That's tied to the actual phase transition, if one exists. Okay? And if one exists, then nu must be greater or equal to 2 over d. That was proven by Lincoln and Jennifer Chase and Tom Spencer and Daniel Fisher in '86. So that's has been a very influential result. That's again, it comes as an important test, right? So if you see a disordered system and somebody tries to tell you that nu is 1/2 in 3 dimensions, you can instantly say that can't be right. Okay. So that these are very powerful results because they are rigorous. So coming back to our exponent relations. So now at a quantum critical point where we have these extra exponents, so how are they related to one another, and how many are independent? So you can go through now and classify things with respect to how many dynamical exponents there are. And in general, so for the purpose of our magnet, we know there must be 2. One that's related to the critical behavior of the magnetization, and one that's related to the fermions. And so now you can go through various homogeneity laws, derive relations between the exponents again. So it turns out Widom and Fisher Widom and Fisher turn out to still hold. And it turns out analogous relations hold for the temperature exponents. So gamma T and beta T are related to one another via delta in the same way in which gamma and beta are related. And the same is true for the Fisher relation between gamma and nu. Okay, if you give them a little cap T index, then they still hold. But other relations change. So for instance, SM Fisher becomes more complicated. And in the case of two dynamical exponents, one for the order parameter and one for the fermions, it turns out that alpha, which is now alpha bar, because it's the specific heat coefficient exponent, plus 2 beta plus gamma is given by nu times the sum of the two exponents. Okay. And for the cap T exponents, it's even more complicated. So instead of SM Fisher, which would be a 2 here, one gets 2 plus a correction term. That correction term, interestingly, goes away if there's only one dynamical exponent. But in general, the right-hand side is not 2. Okay. One can also go and revisit the rigorous bounds. So, for instance, it turns out the Rushbrook inequality still holds, but it holds for the cap T exponents. It doesn't hold for the ones at 0 temperature. Okay, so this is what we are used to from classical thermodynamics, the Rushbrook inequality. If you want to do it at 0 temperature for alpha, bar, beta, and gamma, then it turns out to be greater or equal than 2 beta over beta T, rather than 2. Okay, so there are all these modifications to the known results. And at the end of the day, oh yeah, hyperscaling, of course, also comes into play. It's less useful, again, because our upper critical dimension tends to be so much lower, but let's record it anyway. So there is a hyperscaling relation between the specific heat coefficient exponent alpha bar and the correlation length exponent, and that interestingly depends only on one of the two dynamical critical exponents, namely the one for the fermions. C stands for specific heat here, not for critical. So it turns out that thing just doesn't couple to the dynamical Z that describes the order parameter. And there's another one that relates the alpha bar T to 1 minus D over CZ. And again, one has to be careful with these. They tend to be useless for quantum phase transitions. But anyway, here they are. Okay. So if you then finally count and check how many independent ones are there, then you find there are at least 2 independent static critical exponents. Well, that's pretty obvious because that was the case even classically. And in addition, we need now to consider at least one dynamical one because we can't decouple the statics and the dynamics. And then in addition, there may be other dynamical ones. And so in general, it's complicated. There may be as many as 5 independent static exponents. And if you want to look at the details, then we've written a paper about this. Yeah. Sure.
SM Fisher,
yes.
You have the dimension appearing explicitly, but that is true for any dimension. So there's no
in the generalization of S here.
Yeah, the second line. Yeah.
Okay. Okay.
So you have D appearing explicitly, in the hyperscaling relation.
Okay. This holds under very general scaling assumptions. This holds under slightly more stringent scaling assumptions. So one has to be careful as to what exactly one assumes here about the scaling. Yeah, good point. Thank you. Thank you. in the paper, actually, we distinguish between strong scaling and weak scaling for exactly that reason. So there's at least three different classes. There's strong scaling, weak scaling, and hyperscaling. Okay, so one has to be careful. It's tricky. You're right.
Another question, Dietrich.
Yes.
What happens if you apply this to the Neumann model, let's say the transfer speed Ising model without disorder, just
Okay.
because there we have the mapping to a deep classical model in one higher dimension.
Yes.
So then, how can the dimensionality show up? Because in the Ising model, it would never show up.
The Z's are this. There's no
Z is one in this problem.
Yeah,
right?
that's right. There's not more, but there's no two Z's.
But even with this, oh, okay. So I should read this 1 over Z as
1 over 1 minus 1 over 1 is 1. It's 0. Okay, so then it becomes 2.
Right, right.
So,
Also, in cases like this, how do you define the gamma if the specific heat has a gap?
wait.
I mean, sorry, the alpha.
The
your
alpha bar, yes,
Yeah.
yes.
How do you find the alpha bar if away from criticality there's a gap? Because then the specific heat is not linear.
Well, if the specific heat is not linear, then alpha bar is whatever it takes to make the specific heat do whatever it does.
So it's infinity or 0 or something
Yes.
like this?
Yes. Yeah. That can happen.
Yeah.
That can happen. Yeah.
Okay.
That's not precluded here.
Because exponential, right, in the
Correct.
gap phase.
Correct. Yes. Yeah.
Okay,
I
but
haven't.
that's included.
That's
this case,
included. I haven't checked it for that particular case, but yeah, that must work out.
Okay.
I'm pretty sure it does.
Right.
Okay. Yes. Any other questions? Okay. Now, still have 25 minutes left or so. Okay. So, as the penultimate topic here, and for the last one, I won't have time other than an advertisement. Let me talk a little bit about something that I believe is very important and underappreciated, especially in the experimental community, and that has to do with what it takes to actually reliably measure critical exponents. And again, there's an awful lot known about that in the classical community. So Jan and Anneke Sengers actually wrote a very nice article a long time ago in some Mel Green memorial volume that they entitled "How Close is Close to the Critical Point?" And so what the question is meant to convey is, if I'm an experimentalist, as they are, and I want to measure critical exponents, then how close to the critical point do I have to be in order to reliably see actual power laws in order for scaling to work? Okay. And the answer took 20 plus years to sort out in the classical case, and the final answer was, in almost all systems, I have to be depressingly close. Okay. So here is a little graph that uses the order parameter susceptibility in various systems as an example. Above this horizontal line is what it takes above the critical temperature. Here is what it takes below the critical temperature. And here are various systems that go critical. So you see water at its liquid gas critical point. That's kind of the most optimistic message. Above TC, it suffices to go a bit better than 1%, 0.5% maybe, okay? And now you need to say, how do I define this? Okay, so we need to say we want scaling to work to a particular accuracy. Okay, so some decent accuracy, and then that's good enough. If you do it below the critical temperature, then even in water you have to go to 10 to the minus 4 in order for scaling to reliably kick in. And other systems are much worse. Okay, so here is ethane. So above, it takes about 5 times 10 to the minus 4. Below, it takes 10 to the minus 5. In helium-3, it takes 10 to the minus 5. And remember, that's the upper bound of the scaling regime. So you want to start there and then go towards the critical point for 2 or 3 decades in order to do a log-log plot and get your exponents out. Okay? So this is tricky business, and one has to be really, really close. And to make things worse, it turns out that seeing scaling is one thing. Getting the correct exponents out is another thing, because the exponents tend to depend very, very strongly on the value of Tc. And what exactly that is very unobvious. So to illustrate this point, let me go back to a far-away slide that I forgot to put back in here. So early on in the first lecture, I showed you an example of a scaling plot in a classical magnet. Here it is. So that was chromium bromide. And what I want to emphasize, so here you see these nice scaling plots. Okay, so the curves actually collapsed, and they got exponents out to 3 digits. So what I want to emphasize now is here is Tc to 3 digits. If you assume the Tc is just slightly off, let's say it's 32.86 instead of 844, you still get a very decent scaling plot, but the exponents are drastically different. Okay. So a precision measurement of exponents not only depends on how close you are, it also depends on where exactly Tc is, and pinning that down can be really hard. So with that in mind, let's go back to our quantum phase transitions. Here is that example that we've seen before. So the nickel, aluminum, gallium. Okay. So it shows what looks like a pretty nice continuous phase transition. And if you didn't know anything about anything, you would say, well, clearly this is a continuous transition, and nu seems to be 1/2. So this is an example where the rigorous inequality kicks in. This is a disordered system. Chase et al. Tell us that this cannot possibly be the asymptotic behavior. Okay. The asymptotic behavior may still be critical, but it can't come with this nu. Or the asymptotic behavior may be first order. That may depend on how disordered exactly it is, which is not known either. Okay. So again, one has to be really careful here. In MNSI, we saw that the same thing happens. Nu looks like it's 1/2 for quite a while, and eventually the system crosses over to first order transition. Probably the same thing happens here, but that would require more precise experiments. So that's one example. And here's an even more extreme example. Uranium ruthenium silicide doped with rhenium. That's a famous / infamous material that has a weird phase known as the hidden order phase, where it's known that long-range order develops and nobody has a clue what it is. That has been a mystery for 20 plus years. Okay? Still nobody knows what it is. But let's ignore the hidden order for a second. The hidden order actually so happens in U2C2, and it doesn't survive more than about 10% rhenium. And then for higher rhenium content, the stuff actually becomes ferromagnetic. And here are experiments by Brian Maple's group, where you see they tried to map out the phase diagram. And here you see how the ferromagnetic Tc goes down as a function of decreasing rhenium concentration. And so this is the last data point. Okay? And this is a guide to the I linear extrapolation. So if you look at this, you'd say the critical point is known to what, maybe 10%? At best, probably less than that. And here are exponents they extracted from their experiments. So turns out the exponents, I would say the quote-unquote exponents, the nominal exponents, are strongly x-dependent. And so what happens is that delta starts out at something like 2 and winds up at something like 1 in the extrapolation. Beta is on the order of 0.5 within the error bars, pretty much independent of x. And gamma does something completely bizarre. Gamma decreases and the extrapolation is 0. That doesn't make any sense. If I don't have an order parameter such stability that diverges, then I don't have a second order transition. I mean, that a divergent chi is really necessary to have a second order transition. So whatever these things mean, they cannot be asymptotic critical exponents. Well, no wonder, because remember, we were talking a necessary precision of at least 10 to the minus 4 or better, and here we're talking 10% at best. So one has to be, yeah.
Are these exponents the estimates of the thermal transition at that given x?
Okay, that's another can of worms, because these experiments, I mean, the experimental papers tend to not distinguish between what I call beta and what I call beta t. So one has to be careful there too. Yes, yeah, that was one of the motivations for writing that paper. Okay. So in any case, as interesting and groundbreaking as these experiments are, I think we are still very, very far away from being able to measure quantum critical exponents in these systems, especially in these messy solid-state systems. Yeah. Yes, the small t is the x deviation from the critical x.
Presumably you can't really vary by x by,
that's part
by very small amounts. So it must be that.
That's why the pressure controlled experiments are so much nicer, right? It's so much easier to control pressure than chemical composition. And plus with chemical composition, then you run into issues of homogeneity and correlated disorder, and I mean, it becomes extremely messy. Yes, yeah. Yeah. Oh, yes.
So how were they obtained? What is the?
Oh, so what they said is they said we require the homogeneity law to hold to a certain accuracy. Okay, so we want our family of curves to collapse onto one curve within certain bounds. And the bounds, I can't remember the details, but the bounds have something to do with how accurately you want to measure your exponents. So what you say is, suppose I want to get exponents out of my scaling plot that are good to within 10%. Okay? Then I need to require that my scaling collapse is good to something.
So this is independent of what kind of dangerously irrelevant operators there
It's
might
got
be.
nothing to do with theory at all, okay, other than that we know scaling works. Okay? It doesn't matter what the exponent values are or where they come from. All that matters is that there's scaling going on. And in order to reliably see the scaling behavior, how close do I need to be? That was the question. Okay. And then, of course, over the years, that business has gone into overdrive, and then people were flying their experiments on the space shuttle in order to get one more digit to some critical exponent, right? Okay. In classical fluids in particular, they did that, right? They got it so well under control that gravity was the limiting factor, okay? And then they went to the space shuttle. Yeah. Okay. So I think everybody's getting tired. Certainly I am. So let me conclude by just asking a question and not really giving you the answer. Okay. So let me come back to these really interesting experiments I showed you before. Muon spin rotation measuring the local magnetization and the ordered volume fraction. So here are these MNSI results again I showed you before by Tomo Uemura and his collaborators. So this kind of plot is a bit hard to interpret. So let's interpret this in a more intuitive way and see what the plot is actually saying. Look at the left panel here of this picture for a second. So here is a phase diagram, temperature versus control parameter, let's say excess pressure in this case. That looks like MNSI, right? That's what we saw before. Second order transition, tri-critical point, dashed line is first order transition. Okay. Ordered phase, disordered phase. Ignore this for a second. Let's just look at this because that's what MNSI looks like. And here's what they are saying. They are saying if they're sitting at low pressure, so somewhere here, and change the temperature, then everywhere in the ordered phase, the ordered volume fraction is equal to 1, plus or minus, okay, that's experimental errors. And then at the Curie temperature, it drops to 0. Okay, cool. That's what we would expect. That's still true at 9.6 kilobars, which in the case of MNSI would be somewhere here. Okay. But it's not true if we are at pressures that are at or above the tricritical pressure. So 13 kilobars in MNSI corresponds to somewhere here. And as a function of temperature, as you go up from 0 temperature, you hit the first order transition. So let's look at that yellow curve here. There are not that many data points, but it's clear that even at 0 temperature, the ordered volume fraction is only something like 1/2. Right? So half of the stuff down here in that cross-hatched region is paramagnetic volume-wise, and the other half is ferromagnetic. And that's true, if you map this out, that's true in a region that roughly corresponds to this dark red cross-hatched region here. There's also evidence, but weaker experimental evidence, that there are ferromagnetic regions in the paramagnetic phase. So that's the light red single-hatched region here. And what the MuSR people are saying is, oh, that's phase coexistence. There's coexistence of ferromagnet and paramagnet, and that tells us that this transition is actually first order. Now, there's a problem with that. And the problem is, you can go back a long ways. Let's remember our first order transition in, and that's magnets. Let's look at the fluids. I had one, I know that. The magnets will do if I can find it. Okay, here's the magnet. Here it is. Okay. So let's remember in the fluid case. So we have liquid, we have gas, we have critical point. We have the critical isochore. We have a first order transition as we cross that thing anywhere below the critical point. And yes, phase coexistence is a hallmark of that first order transition. But phase coexistence can happen only on the critical isochore. Only on this solid black curve are the free energies of the two phases the same. As you go away from this critical isochore, that's not true. Right? The stuff is either a liquid or a gas. And no, they don't have the free energy, so they cannot coexist. Okay. Now, what's the analog here? The analog in MNSI or any of these other materials where that's observed is that the analog of the critical isochore is, of course, the dashed line. And the experiment seems to tell us that there's phase separation away from what amounts to the critical isochore. That violates basic, I mean, if you take that at face value, that violates basic thermodynamics. Okay? So something is more complicated here than that. There are two possible explanations I can think of. One would be to say, well, maybe the stuff is not in true thermal equilibrium. Yes?
I don't understand why you say violates thermodynamics, because it depends on whether you use the field variable or the conjugate variable.
In the other phase diagram, the fluid phase diagram, you use pressure. It's a pressure temperature thing. So pressure is the field conjugate to the volume. But here it's X, which is the conjugate variable is the chemical potential of difference between the two species. So here you should see phase coexistence across the region, but not in the other case.
Wait. I don't get that. If I take, so I take a temperature pressure phase diagram, okay? And so now I have tricritical point, and now here I have a first order transition.
Yeah, that's fine.
That's fine. But if I go away from that dashed line, the free energies of the paramagnetic and ferromagnetic phases are not the same.
Yeah.
That's all I'm saying.
No, there I agree. But it's that if instead of plotting the pressure, you plotted the conjugate variable, which is the volume, then you would see phase coexistence.
But that's not what they're doing.
I
agree. Sure. Then of course.
Exactly.
I mean, then you get a coexistence region. Yes. But that's not what they're doing.
So the question is, what is on the x-axis that you showed there? Is it a pressure or is it a composition?
Then X. Okay. For the purpose of this experiment, X is P.
Then that's fine.
Okay. Yeah. Okay. Good. Yeah, sorry, I just I pulled these figures out of two different sources, and yes, X is P. Okay, good. So one possibility would be to say, well, maybe the stuff is not in true equilibrium. Yeah, that's possible. However, if you talk to the experimentalists, then it turns out that the MNSI samples they stuck into the muon beam here at Triumph are in 2007 or whenever they did this. They are the exact same MNSI samples that Pfleiderer had measured the susceptibility on in 1997. So for 10 years, they had been sitting on a shelf in Munich, and then they shipped them to Vancouver and did this experiment. Okay? So if it's non-equilibrium, then it must come with a relaxation time that's large compared to 10 years. I can't say that that's impossible, okay? But I would say it's not particularly plausible. And even if that were the case, then it would behave like something like a glass in many ways. There should be glassy aspects elsewhere, okay? And there's no evidence for that. Okay. So I don't think that's a very plausible explanation. The only other explanation we can think of, we being Ted and I, is that inhomogeneities in, let's say, the pressure lead to droplets of the quote-unquote wrong phase within the right phase. Okay? And if you assume that, then you can start playing with length scales and energy balances and ask, is it conceivable that enough of these droplets exist at a reasonable distance from the coexistence curve to explain these numbers? Okay? And so that was the exercise of this paper that's not published yet. And I think it's a very interesting question, so we gave it a first shot, and we've got to see what happens in the future here. Yeah.
Of course, you would expect that you see effects of these droplets in other modalities too.
Correct. And
I know there's no compelling evidence.
there's no compelling evidence. However, you do find experimental papers where they mumble about pressure inhomogeneities. Yeah.
This volume fraction
Yeah.
is based on some fitting of the muon polarization. How reliable is this claim of phase coexistence anyway? This is some...
No, I mean, it's not a... Okay. So what they measure... And okay, there's of course resolution limitations. Okay, so what they can say is when the decay products come out, what they can tell is whether the muon has been in a spin polarized environment or not. And there is certainly a lower limit to that, to the size of that environment. It must be larger than something in order for that to happen. I have had a very hard time getting hard information on that spatial resolution. I suspect it's on the order of 50 angstroms. Okay, so if the region is less than 50 angstroms, then they probably can't see it. But that's what they measure. So it's a local probe of spin polarization, and then they add that all up. And then that's how they say this and that fraction of the volume is magnetically ordered, and the rest is not. Oh yes, and I should acknowledge my colleague John Toner, because he was the one who really insisted that something is extremely weird here after hearing a talk by Tomo. So, okay, good. So the two of them got into a fight over dinner, and then Ted and I sat down and started thinking about this. Okay, so that's enough. And let me just summarize. So here's what I've been trying to convey. The quantum ferromagnetic transition in clean metals is generically first order because of this fluctuation-induced first order phase transition business, soft modes in the Fermi liquid, and so on and so forth. So that's what I just said. The generic soft modes are clean analogs of the diffusons that we all know and love from the localization business. What's behind this is that the Fermi liquid can be understood as an ordered phase, and it comes with Goldstone modes, and that's what these things are. And as a result, we get generically a tricritical point in the phase diagram because the soft modes don't survive too high a temperature. And so then that comes with tricritical wings and all that stuff. We've discussed a lot of experiments. Quench disorder leads to a crucial sign change of the effect, and that makes the transition second order again, and then we get other complications that Thomas has been talking about that are very interesting. We've seen that in order to even talk about quantum critical points, we need more critical exponents than for the classical case. And I've tried to make the point that the true critical behavior is hard to observe in any system. And in classical systems, it took a long time to appreciate and overcome that. And I would say in these solid-state quantum phase transition systems, we are nowhere near that point, and not even at the point where it's really appreciated. And finally, there is this phase separation business that requires an explanation. And if you want to read more about the general things I've been talking about, here is some suggested bedtime reading. So here is our review on the quantum ferromagnets, where you'll find a lot of the examples I've been discussing. With Thomas, we wrote a review on generic scale invariance in many different systems about 10 years ago. Quantum phase transition, Hertz's paper, of course, is still a classic, so that's a must-read. And Subir Sachdev wrote a book on quantum phase transitions. And then scaling and the renormalization group in general, that, of course, goes back much longer. There's a gazillion good articles and books, and here are just a few of them. Thank you very much.